I want you to imagine something for a second. It's kind of a nightmare scenario, really.
Okay.
Let's say you decide to, better yourself. You take 3 months off to go to a culinary school in Tuscany.
Sounds pretty good so far.
It's amazing. You're mastering risotto, you're hand-rolling tortellini, you know the perfect hydration for focaccia. You're an expert.
Living the dream.
You are. But then you fly home, you walk out to your car, you sit down in the driver's seat, and you just freeze.
Oh.
You look at the steering wheel, the pedals,
Yeah.
and you realize you have absolutely no idea what they do. You've completely forgotten how to drive.
That would be a neurological emergency.
Exactly. The new skill, the cooking literally overwrote the old skill, the driving in your brain. For a human, that's a tragedy. For AI, that's just a regular Tuesday.
It is. It's the fundamental flaw that I think keeps a lot of engineers up at night.
We're talking about catastrophic forgetting. It sounds dramatic because, well, it is. And for the longest time, it's been the dirty secret of large language models. You teach them something new, and they just cannibalize what they knew before.
It's the #1 reason enterprise AI is so difficult to scale right now. You want a model that learns and remembers, but usually you have to pick one.
But that reality might be shifting. We're looking at a breakthrough paper that just came out of MIT, specifically the Improbable AI Lab and ETH Zurich.
Yeah, this dropped around February 11th, 2026, so it's fresh research. And they aren't just trying to patch a bug. They're proposing a whole new way for models to learn.
And the method is called Self-Distillation Fine-Tuning, or SDFT.
SDFT, right.
The promise here is huge. It's about moving from an AI that's, frozen in time, a static snapshot, to one that's a lifelong learner.
Which is pretty much the holy grail.
So to really appreciate the cure, I think we have to properly diagnose the disease. Why are these billion-dollar AI brains so bad at holding on to new information?
Well, it really comes down to how we train them. Right now, if a company deploys an AI, that model is frozen. It knows what it was trained on, and that's it. So if you launch new product line next week or your compliance laws change, the AI is completely oblivious.
It's a time capsule.
It's a time capsule, exactly. So to update it, you have to fine-tune it. And we basically have 2 ways to do that, and frankly, both have fatal flaws when it comes to this forgetting problem.
Okay, let's break them down. Option A is the industry standard, right? Supervised fine-tuning, or SFT.
Right. Think of SFT as just parroting. You give the model a big data set of perfect Q&A examples, these expert demonstrations, and you just say, memorize this, mimic this.
Which seems logical. Here's the textbook, learn the facts.
It works for injecting facts, sure, but it's what we call off-policy learning. The model isn't trying to solve the problem, it's just trying to parrot your text. It's rote memorization.
Okay.
And because these neural networks have limited capacity in their weights, when you force-feed it this new textbook, it adjusts its weight so aggressively that it just overwrites the old ones.
And there's the cooking overwrites driving moment. It optimizes for the new thing and just destroys the old thing.
Precisely. That is catastrophic forgetting in a nutshell. So because of that, engineers often turn to option B reinforcement learning, or RL.
This is the trial and error method, like training a dog with treats.
In a sense, this is on-policy learning. The model tries to generate an answer, it fails, and it gets a reward score based on how well it did. It learns from its own struggle.
And we know RL is amazing for things like math or coding.
The gold standard. And why? Because code either runs or it doesn't. There's a ground truth. You can write a little function that says, if the code works, give the model a cookie.
Right. But most of the business world is not code.
Exactly. And the source material uses a great example here. Imagine you want an AI to write a legal brief or maybe summarize a chaotic meeting into a polite email.
Okay.
How do you write a mathematical equation that scores how good or polite a legal brief is?
You can't. It's subjective. You'd need a person to grade every single attempt, which just isn't scalable.
It's fuzzy. And there's an even bigger problem with RL that one of the MIT authors, Aiden Schenfeld, points out. It's the zero-knowledge problem.
This is the part that really clicked for me.
It's a simple concept, but it's a hard barrier. If you're trying to teach an AI about a brand new product line, something that literally didn't exist when it was first trained, RL just falls apart.
Because the model has no way to even guess the answer.
Right. I mean, if the model knows nothing about your new product, it can guess for 1,000,000 years. It will never accidentally hallucinate the correct technical specs to get a reward.
It's like asking me to guess your Wi-Fi password. I can try forever, but unless you give me a hint, I'm never getting in.
Exactly. So we're stuck. SFT works for new facts, but makes the model dumb about everything else. RL works for skills but fails if the task is subjective or the model starts from zero.
So, enter the hero of our story. Self-Distillation Fine-Tuning, SDFT. The claim is that it bridges this exact gap.
It does. It basically combines the best of both. It uses the mechanism of mimicking, like SFT, but it's applied in a loop that feels a lot more like reinforcement learning.
Okay, let's unpack that name first. Self-distillation. That sounds like the model is, what, extracting knowledge from itself? How does that work if it doesn't know the answer?
This is the really clever part. It weaponizes something that modern LLMs are already surprisingly good at: in-context learning.
In-context learning. That's just the model figuring things out from the prompt itself, right? Like when I paste a weird document into a chat window and say, summarize this, and it just does it.
Exactly. It wasn't trained on that document.
Yeah.
It's just using its short-term memory, the context window, to figure it out on the fly. But that learning is temporary.
As soon as you close the chat, it's gone.
It's gone. So SDFT is all about taking that temporary in-context ability and burning it into the model's permanent memory.
So walk me through how they do that. The paper describes a teacher and a student, but they're the same model, aren't they?
They're versions of the same model. So here's the setup. You have two copies. Copy A is the teacher, copy B is the student.
Okay.
We give the teacher the test question, but, and this is the key, we also give it the answer key, the expert demonstrations, right inside his prompt.
The teacher is cheating. It has the open book.
It has the open book.
Yeah.
And because of that in-context learning we just mentioned, the teacher can look at those examples, understand the pattern, and generate a perfect response.
Ah.
But not just the response. It also generates the reasoning to get there. It creates what they call a reasoning trajectory.
So the teacher knows what the answer is and why it's the answer. Okay, what about the student?
The student, that's one we're actually training, it gets the exact same question, but no answer key, no open book.
It's flying blind, simulating real life.
Correct. The student makes his best guess. Then, instead of a human grading it, the system just compares the student's guess to the teacher's perfect reasoning. The student then updates its own parameters to be more like the teacher.
I see. So it's not just copy these words like the old SFT method. It's copy this thought process.
Bingo. It is distilling the temporary prompt-based insight of the teacher into the permanent weights of the student. It creates this feedback loop that feels like RL. It's learning from its own attempts, but it doesn't need a reward function because the teacher provides the target.
That is incredibly meta. The model is literally pulling itself up by its own bootstraps.
It is, and because the supervision is coming from the model's own internal logic, not just blindly fitting to an external text file, it turns out to be much, much gentler on the model's existing memory.
Okay, theory is great, but let's look at the scoreboard. They ran benchmarks.
They did. They tested this on the QN 2.5 model, which is a popular open-weight model, and they looked at a few complex skills. Science Q&A, using software tools, medical reasoning.
So how did it do against the standard method?
On the Science Q&A benchmark, the standard method, SFT, hit about 66.2% accuracy. SDFT hit 70.2%. So right away, it's better at learning the new thing.
A 4% bump is nice, but that's not the headline. The headline is the forgetting part.
Right. This is the previous tasks test. When they trained the standard model on science, they checked if it could still answer logic and humanities questions. You know, stuff it knew before.
Yeah.
The standard model collapsed. Its performance just cratered.
The risotto problem. Learned science, forgot poetry.
Exactly.
Mm.
But the SDFT model, it learned the science, but it kept its previous task score steady at 64.5%. It barely moved.
Yeah.
It didn't lose the old skills.
Yeah, that is the game changer. But there was one experiment in the paper that I found absolutely fascinating, the 2025 Natural Disasters Test.
Oh, this was brilliant. This really gets at the difference between memorizing and actually understanding.
So tell us what they did.
They basically gaslit the AI. They made up a data set of fake facts about natural disasters that happened in 2025. You know, floods, earthquakes, things that haven't actually happened.
So they're injecting this brand new fake knowledge into the models.
Right. But here's the genius part. They didn't just ask what happened in 2025. Any parrot can spit that back out. They asked indirect reasoning questions.
Give me an example.
Something like, given the floods in 2025, which countries likely needed humanitarian aid?
Ah. So the text says, there was a flood in region X. The question is about aid. You have to know the fact and then apply logic to it.
Exactly. You have to understand the implication of the flood. And the standard SFT model, it failed. Hard. It had memorized the facts, sure, but it couldn't use them. It failed the reasoning test.
And the SDFT model
Scored 98%.
98%. That is a massive gap.
It proves that SDFT didn't just paste the information in, it integrated into the model's reasoning capabilities. It understood the consequences of the new facts.
And this leads to this idea of sequential learning, because you don't just learn one new thing. You learn science, then you learn to use a tool, then you learn medicine. You stack them.
And that's exactly what they tested. They stacked these tasks one after another. With the standard model, it was a seesaw. It would learn science, then forget it to learn tools, then forget tools to learn medicine.
One step forward, one step back.
But the SDFT model successfully accumulated all three skills. No regression.
So if we zoom out to the enterprise world, what does this actually mean for, say, a bank?
Well, right now, most big companies are managing what some people call model zoos.
Model zoos, I like that. A cage for the HR model, a cage for the legal model.
It's exactly that. You have a different model or adapter for legal, another for coding, another for customer service. It's expensive, it's inefficient, it's a huge bane to maintain.
And the vision with SDFT is to, what, kill the zoo?
The vision is a single generalist model that just accumulates skills over time. Schenfeld notes this leads to a substantial reduction in inference costs. You just query one model, it knows legal protocols and coding standards.
That sounds like a dream for any CTO, but there's always a catch. Nothing in AI is free.
There are always trade-offs. And the first one is cost, specifically training cost. SDFT is not cheap to run.
How expensive are we talking here?
The paper says it's about 4 times slower than standard fine-tuning. And it requires roughly 2.5 times more compute power, more FLOPs.
Ouch. Why is it so much heavier?
It's because of that loop we talked about. In standard tuning, you just feed data in. It's passive. With SDFT, the model has to actively generate answers, what they call rollouts, during training, just to compare against the teacher.
And that generation takes time and power.
A lot of time and power. So you pay more upfront to train, with the hope that you save later on inference and flexibility. It's an investment.
But there's another barrier you mentioned from the paper, the smart enough barrier.
This is crucial. The whole system relies on the teacher model being smart enough to figure out the right answer from the prompt, right? Using that in-context learning.
Right.
Well, if your model isn't smart enough to do that, if its in-context ability is weak, then teacher gives bad advice.
And the student learns garbage.
Exactly. They found that smaller models, around 3 billion parameters, they really struggled with this. They just weren't intelligent enough to be their own teachers.
So this is only for the massive, heavy-duty models.
For now, mostly. But Schenfeld did mention that newer architectures are changing this fast. The Quinn 3.4b model, which is still pretty small, was strong enough. He expects even 1 billion parameter models will get there soon.
Things are moving fast, and for the developers out there listening who want to try this, is it locked away in an MI2 lab?
No, actually the code is already up on GitHub, and they're working with Hugging Face to get it integrated directly into their main libraries. So it should be pretty accessible very soon.
It really feels like a shift in philosophy. We've treated AI training like building a statue. You chisel it, you polish it, and then it just sits there. This feels more like raising a child.
That really is the big picture here. Lifelong learning. We're moving away from these static snapshots of intelligence, and it lines up with where the whole global compute market is heading.
How do you mean?
Well, think about where all the energy is going. We hear a lot about the massive cost of training these models, right? The big GPT-4 runs. But actually, most global compute now goes to inference, to actually using the models day to day.
Just answering all our queries.
Right. And SDFT is basically saying, hey, let's harness that inference capability, that ability to think on the fly, and use it to make the model smarter.
So it harnesses the daily grind to improve the mind.
That's a great way to put it.
So here's where it gets really interesting for me, and maybe a little unsettling. If the model is creating its own feedback loops, at what point does it stop needing us to, curate the curriculum?
That is the question. I mean, right now, we still provide the demonstrations, the answer key for the teacher. But if that teacher model gets robust enough, and it can start generating its own reasoning from just very sparse data.
The line between human-guided learning and, well, self-evolution gets very blurry.
Gets very blurry. We might eventually just be the ones turning the lights on and off.
A provocative thought to leave you with. If you want to dive deeper into the actual charts and the methodology, we have linked the paper in the show notes. It's definitely worth a read.
Absolutely. It's a dense read, but a very rewarding one.
Thanks for listening to this deep dive. We'll catch you on the next one.